Hello everybody, hope you have finished the previous topics. The last topic we had discussed about the colligative properties of the dilute solution. So we had studied with four colligative properties and the mathematical expression for them. The first one of them was relative lowering of the preparation. The next one, elevation of boiling point. Third one, depression of freezing point. And the fourth one is osmotic pressure. Now today we are going to discuss about the abnormal behavior of the solution. Abnormal behavior of the solution. What is abnormal behavior of the solution? Suppose any one of the colligative properties of a particular solution if we measure, then the expected value and the observed value in case of certain solutions are found to be different. Okay, let us elaborate it a little bit more. Out of these four colligative properties, the most easily measurable colligative property is osmotic pressure. That can be very easily measured, osmotic pressure. So let us talk about this osmotic pressure. The same can be applicable for relative lowering of vapor pressure or elevation of boiling point or depression of freezing point. Suppose a solution of 10 gram of sodium chloride and that is dissolved in suppose 1 liter of solution, dissolved in a solution, and the volume of the solution is 1 liter suppose. So now if I ask you that to calculate the osmotic pressure of it, so theoretically you know the value, you know the equation. So the osmotic pressure will be equal to what? Osmotic pressure will be equal to W2. What is W2? How much gram we have taken? 10 gram into R. What is R? 0.082 liter atmosphere per Kelvin per mole. We know the value of R. Into temperature, suppose it's happening at 27 degrees Celsius. This is at 27 degrees Celsius. So it's 300 Kelvin. 300 Kelvin divided by M2. What is the molar mass of sodium chloride? Molar mass of sodium chloride is 35.5 plus 23. So that is equal to 58.5 into V is 1. So you can calculate this value. Whatever value. Suppose very easily we can find this value, and suppose this value is X. Obviously the unit will be atmosphere, X atmosphere. Since we are taking the value of R as 0.082 liter atmosphere per Kelvin per mole, so the value of pi will be X atmosphere. So that's how did we get it? We get it by pen and paper. That means we got it by theoretically. So this is a theoretical value. Now I told, take this solution, go to the lab and measure its osmotic pressure. You have the instrument, you can measure the osmotic pressure. So you tried to measure the osmotic pressure and you found the osmotic pressure of the same solution, which I am writing as practical, and you found very surprisingly that is equal to 2x. Suppose this is, you got 10, so you got the value 20, which is not expected. The expected value is 10, but the practical value you got 20. Why? Here comes the abnormality. It can be greater. It is not necessarily that it will be doubled. In this case, it is doubled. It can be tripled. It can be 1.5. It can be 1.9. It can be 2.5. Whatever. It is increased. In certain other cases, it might even decrease than the expected values. Now, why this increase or decrease is taking place? For understanding that, we have to go back to the definition of the colligative properties, to the concept of the colligative properties. What is colligative properties? What did I say? That the colligative properties are the physical properties of the dilute solution, which depends on the number of solute particles, but not on the nature. Here is the trick. It depends on the number of solute particles but not on its nature. Now, how can we explain this? Say this. I told you we are adding sodium chloride. So we are thinking we are adding sodium chloride as a molecule. So suppose 10 gram contains whatever molecule, suppose X molecule 10 gram contains X molecule of sodium chloride. So we are calculating theoretically for X molecules of sodium chloride. But in actual practice, what is happening? Whenever we are dissolving this sodium chloride, it is getting dissociated into Na positive and Cl negative ions. Now that one particle of sodium chloride before the solution is prepared is converted into or is broken down into two particles. Doesn't matter what are the particles. It is iron, but it does not matter. So obviously, practically, the number of particles is no more x, it is 2x. And because of number of particles is more, its practical value is found to be more. This particular phenomenon of abnormality is called association of solution. So this abnormal behavior is because of what? This is called dissociation. This is called dissociation. So the abnormal behavior is because of what? Because of dissociation of the solute particles. So if the solute particles are dissociated, the number of particles in the experiment is getting greater than that of the expected one. Suppose we are thinking of one particle, but it is broken down into 2 or 3 particles, or maybe 1.5 particle, whatever. So it will be greater. Since it is greater, so all the colligative properties value will be found greater than the expected value. Same way, in certain cases, suppose in certain solution, for example, suppose acetic acid, CH3, COOH. If I add acetic acid in water, suppose I am thinking that I am adding 2 molecules of acetic acid and we are calculating according to that. But when it is going to water, these 2 molecules is becoming one particle. It is as a whole is becoming one particle. That is called dimer. So it is undergoing association. We are calculating theoretically for 2 particles, but practically we are getting for 1 particle. In this particular case, the value, that is the colligative property value, will decrease. And this decrease is due to what? Due to association. So the abnormality is because of what? The abnormality is because of dissociation and association. So all these equations we had used needed the rectification, and this rectification of these equations was done by again Van 't Hoff, who introduced a term called Van 't Hoff factor, and is denoted by I. So I, the Van 't Hoff factor, is nothing but the abnormal value divided by normal value. Abnormal value means what? To be understanding it better, it's nothing but practical value divided by theoretical value. So the value of I, if the dissociation takes place, obviously the practical value is greater than the theoretical value. In that particular case, the I is greater than 1. So for dissociation, I is greater than 1. And in case of association, the practical value is less than that of the theoretical value. And for that case, that is for association, the value of I will be less than equal to 1. Fine. Now, the value of I can also be represented as, no confusion, absolutely no confusion should be there. While I am writing abnormal value divided by normal value, in book you might be seeing it as normal molecular mass divided by abnormal molecular mass. Generally, where the confusion comes, sir, you had written abnormal by normal. In the book there is written normal by abnormal, but you don't see the next words. That's the problem. I had written over here abnormal value divided by normal value. But in the book it might be written as normal molecular mass in certain books divided by abnormal molecular mass. That is important, value and molecular mass. Now see all the expression. See all the expression of the colligative properties and see where the molecular mass is there. Molecular mass of the solute is there. You can see the molecular mass of the solute in all the expression are present in the denominator. So whenever I am writing the abnormal value, its molecular mass is coming at the bottom. So abnormal molecular mass is coming at the bottom and normal molecular mass is going in the numerator. So both are exactly same, only the way of expressing is different, and these words I wrote are very, very important. Hope you understood that. What is I? What is Van factor? This factor now introduced in all this equation, and all these equations of colligative properties is converted into, or is just changed into I into this, I into this, I into this, I into this. I is the Van factor. Now the value of Van factor equal to, does it mean that all the solutions are behaving abnormally? No. Those solutions which are not undergoing any dissociation or association are obviously behaving absolutely normally, and for that the value of I is equal to 1. For example, if I take sugar in water, it is neither associating nor dissociating. So for that case I is equal to 1. So if you put I is equal to 1, it's behaving absolutely normal, its practical value and the theoretical value is same. Otherwise, if the association takes place, the value of I is less than 1. If the dissociation takes place, the value of I is greater than 1, and accordingly the colligative properties will vary. So this is all about abnormality, and this is all about the theoretical part of the first chapter, that is solution. I am going to end my class here only. In the next class, we are going to do with some numericals related to colligative properties. Thank you.